So I have a number of questions if nobody else has anything they want to start with.
Please.
So I want to talk about sectioning samples and sort of what sorts of samples are appropriate for sectioning, how deep those samples can be, and things like that. My work is usually in reverse engineering commercial products. So
Okay.
these are finished parts that might have, you know, 50 micron of overglassing on them or something like that.
So I have dealt with samples like that. Typically, the client will initially polish down that top 50 microns to as thin as they can, maybe 10 microns. We can cut through the 50 microns, but again, it's going to be time and cost prohibitive. So
When you
we
say cost prohibitive, what do you?
we charge by the hour, so it's
Right,
much longer time to cut through 50 microns of material versus if you can polish it down to 10 microns or less.
got it.
So um, naturally, we would like it to be conducting, but if it's not conducting, um, there are ways to work around that. But yeah, we ask that you do polish it down as much as possible, both for your benefit and ours. So that can be done through like embedding your sample in epoxy first and then polishing it down. Some
Sure.
other techniques. Okay, I'm seeing a couple questions come into chat. Let's see what we have here. Cryo mode. We do not have cryo mode. However, there is a new cryo fib that was just installed, but I don't think it's actually open to the public. I forget the professor's name, but there's a brand new cryo fib and Titan or Cryos TM that was just installed. And you'll have to get back to me personally if you want their information, because it doesn't come to mind right now who that is. But no, we do not have any cryo on this system. Is it able to prepare cryo EM samples under liquid nitrogen? Again, you'll want to refer to this other professor who just installed a system for doing cryo type work. For magnetic thin films, how thick can the layer be? Off the top of my head, I would just say it would be lovely if it was under a micron. Basically, when we go to some of the higher quality imaging modes with the SEM, if your sample is highly magnetic, the sample could fly up and hit the pole piece. It will just, there's a strong interaction between the electron beam and the magnetic materials. So as long as it's thin enough that it's not a huge magnetic effect, we should be okay. I am willing to try, reasonably thick films of a micron or two. I have done actually bulk samples of magnetic material, sometimes to detrimental effect. In general, we try to avoid the magnetic stuff, but we can work with you. We can work with you or develop a better way of securing your sample in the SEM system.
From a process and access perspective, with the NanoLab CNSI merger, what's sort of the future of the instrument? Is the instrument going to be moved to EICN?
That is not clear at the moment. For the foreseeable future, I would say at least 1 or 2 years, there will be no movement. So I don't think that's a concern of right now.
When we're using the instrument, does it count as both instrument time and NanoLab time for billing?
Thank you for bringing that up. So one of the unique features of this system is because it's not in the clean room, you do not need to become a NanoLab member to use this. So there is no lab time when you're using this because you're not in the clean room. While it would be great for you to become a NanoLab member first to use our system, I do have a large number of clients who are not NanoLab members who just use this system exclusively without using any of the other NanoLab equipment.
So you don't trigger the nanolab minimum billing amounts or any of
No,
that?
no,
Nice.
no.
Do I need to set up a separate billing account with you in order to do that?
If you are a UCLA member.
I I'm a no. I'm a industry
Okay,
user.
then we would just need a purchase order. You would need to set up a purchase order with me. If you're a
All right,
UCLA user, you would just need a recharge ID.
got it.
How high is the resolution for metals? I will need some clarification on that. I'm not sure what exactly you mean by that. Can you talk about the effect of the gallium ions on samples? Can sample get damaged during the ion milling at all? Absolutely. So ion milling is a damaging process. I mean, that's the whole point. You are trying to damage your sample to cut a hole into it or to polish it. So let's see, maybe I can go to a image. So all of this is damage. It's when you're using this system, it's about directing that damage and minimizing the damage to areas that you don't want to damage. This is an area we did want to damage. I wanted to remove all this material. Now the surface, we want it to be undamaged. So we do a final cleaning process at a lower current, or sometimes even lower energies to minimize the damage to the area that you actually want to view. Other damage you may be referring to is implantation of the gallium ions, and that's always occurring. It's minimized though because the material that is getting implanted with your gallium ions is also getting milled and sputtered away up and out of the sample. So there's always going to be implantation of gallium ions throughout the sample, but we can minimize that, especially when you're doing cross sections and TM sample preparation by going to lower energies and so on and so forth. If I'm not answering your questions, please feel free to let me know and follow up.
I've seen some people do tomography with FIB by sort of collecting a whole bunch of samples and a whole bunch of cross sections in a repeated sort of automated way.
Sure.
Is that something that you can do?
So that's referred to, I believe, as a slice and view.
Yeah.
Where you would take one slice, you would take the picture of this, and then you would cut forward some distance and take another picture. And then you'd be able to compile those into a three-dimensional reconstruction of your sample. We can do the initial steps. In other words, I can do a cut, take a picture, do another cut, take another picture, et cetera, and so forth. We don't have the suite of software to recombine those images into a 3D model. But absolutely, we have users who want to see a series of photos along the length. So say I wanted to see pictures along the length of this structure. Very easily, we can cut, image, cut, image, cut, image.
How long does that process take if you were making, cuts on the order of, small, like nanometers?
Are you talking about the step size from
Yeah.
like I guess it's going to depend on how far along you want to cut.
Fair.
If you just want to cut nanometers, the actual cutting time is going to be negligent to go just one step forward. It's going to be the imaging time and refocusing each time. It's a difficult question to answer just because there's so many variables in that procedure.
Sure.
But I would say an hour or a few hours, I think, is a reasonable estimate.
Per step?
No. Total for depending on how far. No. Per each step, we're talking about like a minute or less, maybe 30 seconds. But it's the imaging and all the things that you do between each step that add up to a more significant amount of time.
Got it.
So a cut like this is, what are the dimensions of it? I didn't put the scale bar on this. But assuming this was roughly 10 feet, 10 microns wide and maybe 10 microns deep. A cut like this is not going to take more than about 10 minutes or so to produce, to give you a general idea. But again, it's going to be material dependent, but that can give you a rough idea. All right, I'm sorry, I'm seeing some more questions come in. Could you please, this is one of the best SEMs on campus, could you please compare it with Zeiss Supra SEM at CNSI ESN? Like in which case, which one is better? My comparison is just by having seen images and having used some of these systems. Really, if you want to see the comparison and if you've used these other systems, I ask you to please come in and we can take a quick look at your samples and I can show you what we're capable of producing. But quality of image is obviously a subjective thing, and so I would want you to be the subjective viewer of those results. Can the ion milling alter the microstructure of the sample, like creating defects? What is the ion bombardment direction in the picture you are showing now? Okay, so the ion beam is coming straight down. We orient the sample so that the surface is perpendicular to the ion beam. So the ion beam is coming straight down into the surface. And again, you are damaging the sample, and you will cause damage even to the final surface you're looking at. That damage will be minimum, but yes, at the atomic scale, there will be damage. In general, you're producing an amorphous layer. Assuming this was all crystalline structure, you are amorphosizing, is that a word? You're making the surface amorphous a certain depth, and that will depend on the ion beam energy. So in general, like when we're producing TM samples, we need to minimize that amorphous or that damage to the surface that's making the surface amorphous. And we'll do that by going to a lower energy ion beam, typically 10 kV or 5 kV, typically 10 kV, maybe down to 5 kV, to minimize that damage to the surface of the cross-section that you're trying to view. If you're just trying to see something like this without producing a TM sample, an SEM can't show you these levels of damage anyways, so we'll just use the higher energy ion beam to produce these cross sections. So it's only really if you're doing TM sample prep that you need to be too concerned with the damage to the surface from the ion beam. Direction in the picture showing, like creating defect. Again, I hope I'm answering your question. If not, please clarify further. Is the platinum deposition a uniform layer or just a specific spot? So the platinum dep, I'm sorry I didn't produce more images. I guess here's like another example of platinum dep. Just like I can tell the ion beam to only cut in this square, basically I will tell the ion beam to only scan in this rectangle. And what's happening is there is a gas that is flowing over the surface of the sample everywhere, but only where the beam scans is that gas decomposing onto the surface, sort of like CVD vaguely. And that, depending on how long I scan in that region, the thicker the platinum will grow, or the more platinum will be deposited. And it's not pure platinum. It's an organometallic gas, so there's a large quantity of carbon as well, so that it's not pure platinum, but it's conducting enough. Uniform layer, just to specific spots. I hope I answered your question, Michael. Will there be temperature effect on the sample when damaging the sample with large voltage current? Good question. And to be honest, I don't have a precise answer for you. In our experience with working with a large variety of samples, we really haven't seen any temperature effects on the samples in terms of melting anything. There are definitely effects that are well known when you're using the system to modify your sample. But temperature itself, I'm not clear on. In general, right, the charge is being grounded away, if assuming your sample is conducting. I'd say the most dramatic effects we see are when you're cutting through photoresist or passivation layer, we'll see a lot of bubbling occurring, but I'm not 100% sure that's due to a temperature effect. I apologize, I don't have a better answer for you in regards to temperature. How thin can you make TM samples? So the joke is that you can make them 0 nanometers thick, right? Basically, you cut until it disappears. Where's my, right? So I can just keep cutting until the material starts to disappear. So here you see this was originally a thick layer of platinum protection on top of the sample, and it starts to come down as we cut and make it thinner and thinner. On average, typically we're making samples less than 150 nanometers. We do aim for under 100 nanometers. Some people who are doing like EDX in the TM, they actually want a thicker sample so that you have more material to collect signal from. If you are just interested in the top thin layers on your surface, and by top I mean under a few hundred nanometers, we can get it down to even 50 nanometers thick. It's when you have large windows that you want to observe that the sample needs to be left thicker before it starts bending around and losing stability. But again, we aim, to answer your question briefly, we aim for under 100 nanometers. And if you have thin layers, and if you're only interested in a smaller top surface area, we can go even thinner. Thank you guys for all these questions. These are very good questions, and there's a lot to talk about with FIB. This was meant to be a brief introduction to it, to stimulate these additional questions, which I'm glad you guys are asking. Where are we at? 11:15. Yeah, if there's no further questions, again, I'll hang around for another 15 minutes or so. Otherwise, thank you all for coming. And again, here is my contact information, and I hope you reach out to me if you need any assistance.